Hello and welcome back to another chemistry tutorial with me, Miss T. Today we're going to be looking at limiting and excess reagents, which is one of the most common questions that I get asked by students. This is covered in A-level chemistry across all specifications and also IB topic 1, so SL and HL. If we start with a reminder about stoichiometric relationships, so the last video and the link is up at the top, the balanced equation tells us the ratio in which the reactants react and the products are formed. And so the coefficients tell us these ratios. When in doubt, we always calculate the moles. So whether we're given a solution, a solid, or a gas, we can use our various expressions to calculate the moles, use the balance symbol equation to determine the ratio, and therefore the moles of whatever it is we are trying to find out. Now, often when we are performing chemical reactions in real life, in the lab, in industry, we don't often use stoichiometric quantity. So we don't use exactly the right number of moles as we want to maximize the yield. To make as much product as possible, we'll usually add one of the reagents in excess, so add more than we need to make sure that we get as much product as possible. And so in this video, we'll be looking at calculating which substance is in excess, which is the limiting reagent, so the one we don't have enough of, and therefore how much product can we make. So worked example number 1, we've got 25 centimeters cubed of 0.0150 moles per dm cubed of HCl reacting with 20 centimeters cubed of 0.02 moles per dm cubed NaOH. Which reactant is in excess? So when in doubt, calculate the moles. So we'll calculate the moles for each of these using moles equals concentration times volume. So for HCl, concentration times our volume, making sure we've turned that volume into decimeters cubed, we get 3.75 times 10 to the minus 4 moles. For our sodium hydroxide, 4.00 times 10 to the minus 4 moles. So looking at our balance symbol equation, it's a 1-to-1 ratio. So it's really obvious the excess reagent is whichever one we've got more moles of, which in this case is the sodium hydroxide. So for our next worked example, 50.0 grams of SO2 reacts with 20.0 grams of O2, which is in excess. And we're given the balance symbol equation. Again, first step, when in doubt, calculate the moles, and we're given masses, so we're going to use moles equals mass over MR. For SO2, that gives us 0.78 moles, and for O2, that gives us 0.625 moles. Now here, it's not a 1-to-1 ratio, it's actually a 2-to-1 ratio, so it's not quite as simple as the last example, where we just compare which number is the biggest. Instead, first, we need to divide the number of moles for each species by its coefficient. So for SO2, we'll do 0.78 divided by 2, as that's its coefficient in the balance symbol equation. And for the O2, we'll divide 0.625 by 1, as 1, which is invisible in the balance symbol equation, is the coefficient for O2. And so we end up with 0.39 for SO2 and 0.625 for O2. Now we can see that 0.625 is larger than 0.39, and so the oxygen, the O2, is in excess. Okay, so when the numbers aren't 1-to-1, we have to add that extra step of dividing each number of moles by the coefficient in the balance symbol equation. So for our final worked example, we're trying to calculate how much product we can actually make based on the reactants that we're starting with. To do that, we first need to determine which is the limiting reagent, as whichever is limiting is going to determine how much product we're able to make. Okay, we can't make more than our least number of moles. So first, we calculate the moles of each so we can determine which is the limiting reagent. So our moles of iron, mass over mR, which gives us 1.79 moles. And for our moles of oxygen, mass over mR gives us 1.41 moles. As before, to determine which is the limiting reagent, we have to divide each number of moles by the coefficient in the balance symbol equation. So for the iron, we divide the moles by 4. For the oxygen, we divide the moles by 3. And that shows us that the iron is the limiting reagent, 0.448, versus oxygen is in excess. Now, to determine how much product we can make, we have to use the limiting moles. So we're going to use the moles of iron to determine how many moles and therefore the mass of iron oxide that we can make. Now, really importantly, these new numbers, the ones in purple that we got by dividing by 3 and by 4, we're never going to use those numbers again. Okay, we're going to use our original moles of iron to determine the moles of iron 3 oxide. So iron being our limiting reagent, moles 1.79. We use the balance symbol equation. We see the ratio of iron to iron oxide is 4 to 2, which is the same as 2 to 1. So we'll divide that number of moles by 2 to get the moles of iron 3 oxide. Now to find the mass of iron 3 oxide, we do moles times mR, and that gives us 143 grams. Answer given to 3 significant figures, as that's the least precise piece of data given in the question. Okay, it's your turn. A bit of a tricky one today, so feel free to go backwards, re-watch the worked examples before you give these a try yourself. All of the relative atomic mass values that you need from the periodic table are over to the right. Pause the video and then press play when you're ready with your answers. So first, which reactant is in excess? Well, we'll just calculate the moles for each as mass over mR. It's a 1-to-1 ratio, so the sulfur, as the larger number of moles, is clearly in excess. Next worked example, what mass of ammonia can be formed when 250 grams of nitrogen reacts with 40 grams of hydrogen? So we'll start by calculating the moles of each as mass over mR, and then to determine which is the limiting reagent, we'll divide both of those numbers of moles by the coefficient in the balance symbol equation. So for the nitrogen, divide the number of moles by 1, and for the hydrogen, divide the number of moles by 3. That shows us that the hydrogen is the limiting reagent. So we're going to use the moles of hydrogen to determine the number of moles and therefore the mass of ammonia that we can make. Remember, to calculate this, we now ignore those new values in purple and we go back to our original moles. So our moles of hydrogen that we're reacting with is 20 moles. The ratio of hydrogen to ammonia is 3 to 2. So to find our moles of ammonia, we're going to divide by 3 and then multiply by 2 to give us 13.33 moles. Mass is moles multiplied by mR, and so we get 227 grams of ammonia to 3 significant figures. Now for our final question, calculate the total mass of gas present after 200 grams of iron 3 oxide reacts with 150 grams of CO. So as usual, we'll start by calculating the moles of each as mass over mR. And then we'll divide each number of moles by the coefficients in the balance symbol equation. So for the iron 2 oxide, divide that number of moles by 1. And for the carbon monoxide, divide that number of moles by 3. That shows us that the iron 2 oxide is the limiting reagent. So we're going to use those moles to determine the mass of CO2 that we can make. Now, the ratio of the iron 3 oxide rather, to carbon dioxide is 1 to 3. So our moles of CO2 is 3.75 moles. Mass as moles multiplied by MR gives us 165 grams of CO2. Now notice the question says the total mass of gas. And because the carbon monoxide, the CO, is in excess, that means that there'll still be some left over after all of the iron 3 oxide has reacted. So added to that mass of CO2, we also need to determine what mass of CO will be left as well. To do that, we'll find the moles of CO left over as the original number of moles, 5.36, minus 3.75, as it's also a 1 to 3 ratio. So that gives us 1.61 moles of CO left over. Mass of CO, moles multiplied by MR, gives us 45.1 grams. So now the total mass of gases, your mass of your CO2 plus your mass of your CO, gives you 210 grams to 3 significant figures. So how did you do? Let me know down in the comments, and also if there are any topics that you really want a mini tutorial on, let me know there as well. See you next time. Bye.